Hello. In the last of these short videos about equivalent networks, I'm going to look at an outline proof of Thevenin's theorem. First of all, let's state exactly what we're trying to prove. The idea is that for any linear network, there is an equivalent network which consists of a voltage source with a resistor in series, such that if you put anything between the two terminals of the linear network, the same current would flow and the same voltage would appear across it as if you put the same thing across the equivalent network. Now, let's start a proof. Let's consider our linear network here with two terminals, and we're going to put across those terminals a current source. And if there is an equivalent network, then it would mean that we could produce an equivalent network, put the same current source across its outputs, and the same voltage would appear between the outputs in both cases, since the same current would be flowing out in both cases. The current flowing out would be determined by the current source. That's what current sources do. They force that particular current to flow around this circuit. Okay, this is a linear circuit, and we've added to it a constant current source, which is a linear component. So here we've got an entire linear circuit, and we can analyze the voltage. I'll call it VAB, the voltage between terminals A and B. Can analyze that voltage using superposition. Firstly, we'll turn off the current source. Then we're measuring the open circuit voltage of this linear network. I'll call that V1. That's the first contribution to the total voltage in this circuit. It would just be the open circuit voltage of this linear network. Then I can turn off all of the sources in this linear network and only consider this current source. The second contribution to this voltage between A and B I would get is now the contribution due to this current source. Since this is a linear circuit, the voltage here must be linearly related to this current source. I could write it as K times I. It's just a consequence of the general definition of a linear circuit, that its output, Y, must be the sum over all the possible inputs of a constant times each individual input. Y here is my output VAB, and I'm just looking at the contribution to VAB from this current source here. So that's going to be some constant K times this current source here, current I. The total voltage between A and B, therefore, VAB, will be the sum of these two, VOC plus KI. Now, consider what happens in my equivalent network here, where I've just got a voltage source, I'll call it VTH, and a resistance RTH. If I force a current to flow through this network with this current source, then the voltage difference across this resistor must be the current, I, times RTH. And if the voltage here is VTH, then the voltage at this point here must be VTH minus I times RTH. And that would be the voltage across the terminals A and B in this case. Now, if I compare these, I can see that they are actually the same, provided that my open circuit voltage is my Thevenin voltage, and this constant K turns out to be minus RTH. So provided I pick my constant K and my open circuit voltage as the two constants, the voltage here at the output of this linear network and the voltage here at the output of my equivalent network will be the same for all different values of current source that I put on the output. The final stage of this proof is to realize that any component that I put on the output of a network can be replaced by a current source. I could put a diode here, for example. And if I added a diode to this network, then some current would flow. Well, I could replace that diode with a current source equal to the current that would flow through the diode. And the same current would be being taken out of my network, which means the same voltage will be appearing on the output of my network. It doesn't matter whether I have the diode there or whether I have a current source whose value is equal to the current that is flowing through the diode. And I can do the same trick no matter what I add to the output of my linear circuit. Which means that these two networks are going to be equivalent for any load that I attach to the outputs. The load doesn't have to be linear. Okay, that is the end of this series of talks about equivalent networks.